Okay, in this video, we're going to work a statics problem that falls under the category of particle equilibrium, which just means that any free body diagram that we draw, all of the forces on that body are concurrent. So that means we can draw the free body diagram as just a point if we want, or we can just draw it as the normal body for illustration. Okay, so a scale is constructed with a 4-foot long cord and the 10-pound block D. So this cord is 4 feet long, and this block D is 10 pounds. The cord is fixed to a pin at A and passes over 2 small pulleys. Determine the weight of the suspended block B if the system is in equilibrium when S is equal to 1.5 feet. Okay, so we can just tell based on the nature of this problem that this is going to be symmetric here, right? So like this triangle here, these two sides are equal length, and like so these two angles are the same. So the first thing that tells us is that what we can write down is that so the length of AB is equal to the length of CD, and so, or the length of CB. And so we can say this. So we know that LAB plus LCB plus 1.5 is equal to 4, right? So let's just substitute LAB for LCB. So 2LAB, and then 4 minus 1.5 is 2.5. Okay, so that means that LAB, which again is equal to LCB, this is equal to 2.5 divided by 2. So 1.25. Okay, so now what that allows us to do is we can solve for these angles. We know that they're the same. Okay, and we can do that because we know, like we know that this is 0.5, right? So cosine of theta adjacent is equal to adjacent over the hypotenuse. So theta is equal to, so let's 0.5 divided by 1.25, and then so inverse cosine, so 66.4. Okay, so the key to this problem, one of the keys, is recognizing that this block is going to be resting in the middle here, that this is going to be symmetric. Okay, so what else do we know? Well, we know the weight of this block. So because of that, we know the tension in the cable cord, or the cord here. But this cord this is the same cord. So if we know the tension here, we know the tension in the entire cord. So the tension in the cord, T, we know is equal to the weight of D, right? I mean, just a free body diagram of this, of D. You know, this is all this is connected. So it's kind of, in this situation, this is all one system, one connected unit, right? Weight, D, tension. Some of the forces in this direction, it's T is equal to WD, which is equal to 10 pounds. Okay? So now let's go ahead and do a free body diagram of this roller here. Well, no, not of the roller. That would be a little difficult because you really want to focus on what your free body diagram is and the forces acting on it. Because if I did just this roller here with the hook attached to it, okay, that's fine. But I've got like a distributed load from the cable, and so like as a unit, that's just acting like that, with the weight of the block acting down. So I don't know anything about, so more of what I'm looking for is let's just separate out the cable in this region, right? That piece of cable, let's just take that out and put it in space. So we've got as a unit, you know, like the kind of the net force from this roller here acting down, and then you've got the two forces from the cable acting like that. But they all meet at a point. So what we can do is our free body diagram can just be a dot, right? A particle. So we'll put our coordinate system at the origin at that point. Okay, and so acting down is the weight of block B. Then you got the two tensile forces acting at theta. And we know these are 10 pounds. Okay? So let's just sum the forces in the y. If we sum the forces in the x, we can see we're just going to get the 10 pounds is equal to 10 pounds. So let's sum the forces in the y so we can solve for this WB. So you can get 10 sine theta plus 10 sine theta. So 20 sine of theta is, so sine of 66.4 minus WB is equal to 0. So WB is equal to 18.33. And that is the weight of block B. That's what the question was asking. So that is your final answer.